This is the first video of complex numbers, and in this video I have two main topics that I'll cover. The first is we'll define what a complex number is, and then I'll show you how to do some simple arithmetic operations on complex numbers. And you can read more about this in Greenberg on pages 1108 to 1113. And we'll first use complex numbers in Cartesian form, which is written as z, being a complex number, is equal to x plus I, y. The second topic will be how to operate or defining what exponents of complex numbers are, and related to that are trigonometric and hyperbolic functions. And that's in pages 1115 to 1120 of Greenberg. And an exponent of a complex number, for example, is e to the z, or that's the same thing as e to the x plus I, y. What I'd like you to take away from this video, as well as the exercises in the homework, you'll know what a complex number is, and you'll also know how to do some simple arithmetic operations, as well as use exponents of complex numbers. Now, in middle school, when you started learning algebra, you learned how to solve an equation of the following form. So x minus b equals 0, and using algebra you learned that x is equal to b. And if b is a positive number, then we knew that x is also a positive number. And about the same time, you learned about negative numbers, so that you can solve equations of this form. Right? So this gives x is equal to minus b. So we learned that numbers have on the positive axis as well as on the negative axis. You also learned when dealing with powers, for example, x squared minus b is equal to 0. You learned that this equation could be solved by taking the square root of b, for example. So x is equal to plus and minus the square root of b. So we learned about taking the square root or the nth root of numbers to solve these sorts of equations. So finally, getting to complex numbers, we need complex numbers to solve equations such as x squared plus b is equal to 0. And so that means x is equal to the square root of minus 1 times the square root of b, and the square root of minus 1 is defined as I, or I is defined as the square root of minus 1. So the triple bars here means a definition. Okay, so this is sort of a build-up to the different types of numbers we use. Again, numbers on the positive axis, the negative axis, and finally numbers on the complex plane. So a general complex number is written as, for example, z is equal to x plus I y. So in this equation, x is the real part of z, that is, we would say that the real RE, the real part of z, is equal to x, and y is called the imaginary part. So we have a real part and an imaginary part. You shouldn't read into the meaning, the sort of conventional meanings of real and imaginary. These are just words that are used to describe these different parts of the complex numbers. So the imaginary part is no less true or real than the real part, so to speak. So the imaginary part is, we would denote that as capital IM of z, and that's equal to y. It's the part that's multiplied by the imaginary, or by I, the square root of -1. Also, I'd like to note that the plus sign does not mean addition. Rather, it means that the the imaginary number is a combination of the real and imaginary part. So to make the number complete, it has both, again, the real and imaginary part. We can plot z. So because z has both a real and imaginary part, to represent z in a plot, we need two axes. And those two axes make up what is called as the complex plane. So we could sketch, so the horizontal axis, x, is often used for the real part. It's the real axis, whereas the vertical axis is used for the imaginary part. So x plus iy has an x value of x and a y value of y, and z would be noted by this point. Z is equal to x plus iy. And you'll see that we'll talk about this later, but we can describe this this coordinate also in terms of polar coordinates, where it has an angle theta from the real axis, and it has a length of r from the origin. And also, I should note, I'd like to define the modulus of z, which is equal, it's real, it's equal to the square root of x squared plus y squared, and that's equal to r, the length of r, well, the length of this arm, and that's r. And so the modulus is a real number. Okay, so that does it for some basic definitions of a complex number. Now let's talk about some simple arithmetic. So let's start with addition and multiplication. And those operations are done just like you do with real numbers, but for the solution, you give, well, the solution is given in terms of the real and imaginary parts separated. Okay, so for example, let's consider the sum of z1 plus z2, and using our original description of a complex number. This is our Cartesian description. We have x1 plus I y1 for z1, and then we're going to add z2, which is x2 plus I y2, and that's simply equal to x1 plus x2, that's the real part, plus the imaginary part is I times y1 plus y2. And I'll refer you to page 1110 of Greenberg for a more thorough description of rules, or properties, I should say, of addition. So let's look at multiplication. So here we'll have z1 times z2, and that's equal to x1 plus I y1 times x2 plus I y2. And if we just carry out the multiplication like we would normally, we have x1, x2 plus I x2 y1 plus I y1 x2 plus I squared times y1 y2, and that becomes x1 x2 minus y1 y2, because the I squared becomes a minus sign, and that becomes real. This term becomes real when we square I, so that our real part is this, and then our imaginary part is x2 y1 plus y1 y x2. And that again is the product of two general imaginary numbers. And this is, so the real part is given as the first term in parentheses, and the imaginary part is the part that's multiplied by I. Another concept I'd like to talk about is the complex conjugate. So if z is equal to x plus iy, the complex conjugate is written with a bar over it, is equal to x minus iy. So for a complex conjugate, the imaginary part is negative, or you multiply the imaginary part by minus 1. So for example, if z is equal to 1 minus I, then the complex conjugate, z bar, is equal to 1 plus I. Again, we've multiplied the imaginary part by minus 1 to get the complex conjugate. One aspect of the complex conjugate is that when the product of an imaginary number times its complex conjugate is real. That converts an imaginary number to a real number. So in that case, z times z bar is equal to x squared plus y squared. And that's the square of the modulus. Okay, so we've covered addition, multiplication, and we've looked at complex conjugate. Now let's look at division. So let's consider the quotient of z1 divided by z2. And you'll note that the denominator is imaginary here. And we don't know yet how to deal with an imaginary denominator. So one thing we can do is convert this into an expression involving a real denominator. And we can do that, for example, by multiplying z1 over z2 times 1, where 1 is written as the complex conjugate of z2 divided by the complex conjugate of z2. Right? And that gives x1 plus iy1 all over x2 plus iy2 times x2 minus iy2, that's the complex conjugate of z2, divided by x2 minus iy2, and that gives x1, x2 plus y1, y2 divided by x2 squared plus y2 squared, and that's the real part. And I've run out of room here, so I'm going to go to the next slide. So again, z1 over z2 times the complex conjugate of z2 over the complex conjugate equals, we have a real part, which I wrote down in the last slide, plus an imaginary part, which is y1 x2 minus x1 y1 all over x2 squared plus y2 squared. Okay, so that's how we rewrote this into an expression in which the denominator becomes real, and so the real part of that quotient is given here, and the imaginary part is given here. So we'll revisit quotients in the next video when we look at the polar form of a complex number. But for now, let's move on to another type of operation. Let's look at exponents. So when we take the exponent, or we raise e to the z power, then that's the same as e raised to the x plus I y power, and that's the same as e to the x, which is real, times e to the I y. And so we now need to define what e to the I y is. So one way that we can explore how to interpret this is let's express e to the I y as a Taylor series expansion. And we'll expand it about y is equal to a is equal to 0. So this is the Taylor series expansion of e to the I y about the point 0. So again, e to the I y. So the first term in the expansion is the function itself evaluated at 0. So that's e to the I 0. But I times 0 is just 0, so e to the I 0 is simply equal to 1. So this expression, the first term, is just 1. The second term is the derivative evaluated at point 0, and that's I times e to the I 0, where again that's equal to 1. And then we have to multiply that by y minus a, or in this case, 0. The third term is 1 over 2 factorial times the second derivative, which is I squared times 1, and we get y minus 0 squared. The third term is 1 over 3 factorial times the third derivative, which gives us an I cubed times 1, and then we have a y minus 0 cubed, and so on. And so when we collect the real and imaginary terms, the real terms become 1 minus y squared over 2 plus y to the 4th over 4 factorial. 2 is the same thing as 2 factorial, minus y to the 6th over 6 factorial, etc. Those are the even powers of y, plus I times the imaginary part, which is y minus odd powers of y, plus sums and differences of odd powers of y, and so on. And it turns out, and you may some of you, well, if you looked at a table, you might recognize that the real part is the Taylor series expansion of cosine of y evaluated at 0. And the imaginary part is the Taylor series expansion for sine of y evaluated at 0. So therefore, from this Taylor series expansion, we find that e to the iy is equal to cosine of y plus I sine y. And this is Euler's formula. So this is where Euler's formula comes from. Okay? And so from Euler's formula, well, let me go to the next page. So thus, from Euler's formula, e to the z, again, was e to the x times e to the iy, and that's e to the x times cosine y plus I sine y. Also, from Euler's formula, we can show that cosine of y is equal to e to the iy plus e to the minus iy divided by 2, and sine of y is equal to e to the iy minus e to the minus iy divided by 2. And from this, we can define the cosine of an imaginary number as cosine z is equal to e to the iz plus e to the minus iz divided by 2, and the sine of z as e to the iz minus e to the iz divided by 2i. And I'm noticing I forgot the I above, so we need an I right here. And the numerator for the definition, well, for the sine function, but there's but not for the cosine function. We just have a 2 in the denominator there. So we've shown by taking we've shown how to take an exponent of a imaginary number, and we showed also why e to the iy is expressed as Euler's formula. And then we showed the relationships to cosines of a real number to the exponents of the imaginary exponent, and finally how to take the cosine, what the cosine and sine of an imaginary number is in terms of those exponents. And you might recognize that these forms, well, if we go to hyperbolic functions, hyperbolic functions of imaginary numbers are just like they are with real numbers. So cosh, the hyperbolic cosine of z is equal to e to the z plus e to the minus z divided by 2. And the hyperbolic sine of z is equal to e to the z minus e to the z minus z all over 2. And you'll notice that these equations are similar. And I'll also refer you to pages 1118 to 1119 for more detailed relationships between trig and hyperbolic functions. So this concludes video 1 of complex numbers, where we looked at the definition of a complex number in Cartesian form. We learned how to add, multiply, and divide using this Cartesian form. And then we also looked at exponents and how they related to trig and hyperbolic functions. So I will conclude this video here.